Welcome to Structural Analysis 2 video series. Unit number 2, Moment Distribution Method. Lecture outline: Numerical on Sway Portal Frame, Part 1. Numerical problem as follows. Analyze the portal frame shown in figure by moment distribution method. Draw bending moment diagram. Moment of inertia for column AB is I. Moment of inertia for BC and CD members are 2I. AB column loaded with the 2 kN point load at a distance of 1 meter from A and 3 meter from B. 16 kN point load acting on member BC at a distance of 0.5 meter from B and 1.5 meter from C. Column CD loaded with the 10 kN per meter UDL and length of CD is 2 meter. This is a problem based on sway frame. Now this problem we have to solve by considering frame as non-sway frame. So let first find out fixed end moment. Our sign conventions are anticlockwise positive and clockwise negative. Member AB. Consider B end as a fixed end. Load acting on AB 2 kN point load. So due to load, the fixed end moment will be generated at the end A and B. So MFAB is equal to WAB square by L square. A is equal to 1 and B is equal to 3. So put the value. Load is 2 into 1 into 3 square divided by 4 square is a span of AB is a 4. So is equal to 1.125 kN meter. And it is anticlockwise, so positive. MFBA is equal to minus WA square B divided by L square. So is equal to minus 2 into 1 square into 3 divided by 4 square is equal to minus 0.375 kN meter. Now consider member BC. Keep both end fixed. And find out fixed end moment due to the coming load of 16 kN at each end. So MFBC is equal to WAB square by L square. So A is 0.5 and B is 1.5 meter. So put the value. Anticlockwise moment is positive. So 16 into 0.5 into 1.5 square divided by 2 square is equal to 4.5 kN meter. MFCB is equal to minus WA square B divided by L square is equal to minus 16 into 0.5 square into 1.5 divided by 2 square is equal to minus 1.5 kN meter. So these are the fixed end moment for beam BC or horizontal member BC. Now consider next span CD, and there is a point load acting on span CD whose intensity is 10 kN per meter. So let's find out fixed moment. So MFCD is equal to minus MFDC So is equal to, now there is UDL, so formula is WL square by 12. So is equal to 10 into 2 square divided by 12. So fixed moment at CD is 3.33 kilonewton meter and fixed moment at DC is minus 3.33 kilonewton meter. So these are the fixed moment for each span. Next point is find out relative stiffness. We know the formula for relative stiffness. When condition far end is fixed, the relative stiffness is I by L. The far end is fixed. Now far end is simple and continuous. If B is under consideration, a far end is C, which is simply supported and continuous ahead. So relative stiffness is I by L. Now when far end is simple and not continuous, now for B joined, far end is C, which is simple and not continuous. The formula for relative stiffness is 3 by 4 into I by L. Distribution factor calculations. Consider internal joint, joint B and joint C. First is joint B, connecting member to internal joint B, member BA and member BC. So for member BA, the far end is fixed. So relative stiffness is I by L is equal to I upon 4. For member BC, the far end is continuous. So relative stiffness is I by L is equal to 2I by 2. So total relative stiffness by addition of relative stiffness of BA and BC is equal to 5I by 4. Distribution factor for each member, relative stiffness divided by total relative stiffness. So relative stiffness is I by 4 divided by 5I by 4 become 0.2. Distribution factor for BC member is equal to K divided by summation of K. So K is 2I by 2 divided by 5I by 4 is equal to 0.8. Now next joint C, and connecting member to joint C are CB and CD. Member CB far end is continuous, so relative stiffness formula I by L, so is equal to 2I by 2. And for CD member, the far end is fixed, so formula is I by L is equal to 2I by 2. So total relative stiffness, addition of relative stiffness CB and CD is equal to 4I divided by 2. Distribution factor for member CB is equal to relative stiffness K divided by total relative stiffness 4I by 2, so become 0.5. Distribution factor for CD, relative stiffness 2I by 2 divided by total relative stiffness 4I by 2 become 0.5. So these are the value of distribution factor for each member. Those are connected at internal joint B and C. Next step, moment distribution table. Now first joint is joint A, then joint B, joint C and joint D. Member connected to the joint A is AB. Member connected to joint B, BA and BC. Member connected to joint C, CB and CD. And last member D, member connected to joint D, DC. Now write down their distribution factor for internal joint BA 0.2, BC 0.8, CB 0.5, CD 0.5. There is no distribution factor, the member which is connected to the last joint or end joint. Then write down the fixed end moment 1.125 for AB. Fixed end moment for BA is minus 0.375, for BC 4.5, for CB minus 1.5, for CD 3.33 and for DC minus 3.33. Now do the balancing. Now at now the end joints having a fixed support, so there is no need of a balancing. Now next step is initial moment calculation. So initial moment means addition of fixed moment and balance moment. Now here the end supports are fixed support, so balancing is not required. There will be a moment at end, so balancing moment become 0. Now do the addition of fixed end moment and balancing moment. So we having initial moment same as like a fixed end moment. Now see the internal joint B and C. Now at internal joint B, to maintain the equilibrium, the moment coming from the connecting member over the joint B should be equal to 0. If we add minus 0.375 plus 4.5, it will come out to plus 4.125. That means we have to apply the correction minus 4.125. Now for joint C, the moment coming from the connecting member minus 1.5 and 3.33. If we add these two, minus 1.5 plus 3.33, it will come out to plus 1.83. So to make it 0, we have to apply the correction. That means we have to apply the minus sign, minus 1.83. So this is correcting moment for internal joint. Now consider this correcting moment which is mentioned in the box. So first is for joint B, minus 4.125 into distribution factor of a BA 0.20. It is equal to distribution moment minus 0.825. For BC, distribution moment is equal to distribution factor 0.80 into correcting moment minus 4.125 is equal to minus 3.33. Now for joint C, distribution moment is equal to distribution factor of a CB 0.5 into minus 1.83 is equal to minus 0.915. Distribution moment for CD is equal to distribution factor 0.50 into correcting moment minus 1.83 is equal to minus 0.915. Now carry the half moment at the far end. So minus 0.825 divided by 2 become minus 0.413. Now carry the half moment from C joint toward the far end B. So minus 0.915 divided by 2 become minus 0.458. Then carry the half moment minus 3.3 to the far end. It become minus 1.650. Same way carry the moment from the C joint toward the far end D. Half moment you have to carry. So 0.915 divided by 2 become minus 0.458. So first we did the distribution and then we do the carryover. So this is first iteration. So likewise let's carry out the iterations process. Now let's see at joint B the moment is minus 0.458. That means there is no balance moment at joint B from far end. Now to make it balance we have to add here plus 0.458 moment. So take that as a correcting moment. Only we have to take the positive sign. So that correcting moment into the distribution factor 0.20, we will get 0.092. Now find out distribution moment for BC. So is equal to distribution factor 0.80 into correcting moment positive 0.458 is equal to 0.366. Now consider joint C. Correcting moment will be plus 1.650 into distribution factor of a CB 0.5 is equal to 0.825. Distribution moment for CD is equal to distribution factor 0.50 into correcting moment plus 1.650 is equal to 0.825. So after distribution we have to do the carry over. So carry the half moment at far end. So 0.092 divided by 2 become 0.046. Next carry over from B, carry the moment toward the C. So 0.366 divided by 2 become 0.183. Carry the moment from C toward the far end B, half moment. So 0.825 divided by 2 becomes 0.413. Carry the moment from joint C toward the joint D, half moment we have to carry, so it becomes 0.413. Now after the carry over moment, we have completed second iteration process. Now see at the internal joint B, the moment, there is no any balance moment because the moment coming from BC is 0.413 and moment coming from BA is 0. So to maintain the equilibrium, the addition of these two should be 0, but it is not there. So again we have to apply correcting moment. So correcting moment here is minus 0.413 into distribution factor of BA 0.20, we will get minus 0.083 as a distribution moment. Now distribution moment for BC is equal to distribution factor BC into correcting moment minus 0.413 is equal to minus 0.331. Now distribution moment for CB is equal to distribution factor 0.50 into correcting moment minus 0.183 is equal to minus 0.092. Distribution moment for CD minus 0.092. In the same way we have to do 0.50 into minus 0.183, we will get minus 0.092. Then do the carry over, half moment you have to carry at the far end. So by doing so, we will get the carry over moment for each joint. Now this is our iteration process third. Now after that we have to do the distribution. So for distribution, now consider internal joint. Here we have to apply correcting moment as positive 0.046 and here positive 0.165. So positive 0.046 into distribution factor, we will get the value 0.09 and 0.037. Same way, considering positive value of 0.165 into the distribution factor, we will get the distribution moment 0.083 and 0.083. Now these values are very less, so let's stop here and do the addition of initial moment. Do the addition of all moments, start from initial and do all the add all the values. So we have first final moment AB is 0.717 and for BA and BC minus 1.182 and plus 1.182, and for CB add from initial moment up to the distribution. Our values are minus 3.21231 and plus 3.231, and last value is minus 3.421. So these are the final moment. Okay, so let's stop here. Remaining part will be resumed in the next video. Thank you.